Good afternoon. It is Sunday, May 4th, 2014. This is Jason Horak reporting on the ongoing adventures of the Dodge Daytona electric vehicle. We're going to go over a couple things today. This is mainly a follow-up video to the previous one where we had pulled the motor out and tested it for making the bad noises. And one of the subscribers to my channel had sent me a message and was thinking that perhaps the brushes are all chewed up from the motor after making those noises. So we're going to go ahead and be pulling the brushes today, take a look at them, see how they are, and hopefully they're not damaged, but I guess we'll see. These brushes are the ones that came in the motor when it was refurbished back in, I believe, December of 2012. I think that's about right. Anyway, so I never took the brushes out. I never even looked at them. I just said, okay, they came from net gain from Warfield motor on the rebuilt motor deal, and I just trusted that they had the right ones in there and it was good to go. I had done a burn-in test where I ran the motor for a number of days in order to kind of burn in those brushes before running high current through them, and yeah, they've been working great ever since. So right up until we had this noise recently, the motor's been running like a champ. And again, I took it to EvCon 2013 and ran it on the drag strip out there and beat the heck out of it, and it just worked great. So anyway, we'll go ahead and take that apart. And one of the other things that I'm going to do today is actually remove the pressure plate, clutch, flywheel, adapter plates, and all that other good stuff, because what I have done is gone ahead and purchased another motor. That would be over here, and it has arrived. Now this motor is kind of interesting. This is a net gain Warp 9 motor, just like the other. And actually, this is my original motor that I purchased back in 2010, and which blew up spectacularly at the EvCon 2012 out in Missouri. If anyone remembers from my earlier videos, or if they were there at EvCon, this was the motor that had the rotor that threw a big chunk of the metal inside the rotor had come out, and it just killed it. So it was driving around fine in Cape Girardeau, Missouri, and everything was good until it went thunk, and there was a big chunk of motor missing. George Hamstra took a look at it when we were there, and he had mentioned that he had never seen anyone kill a motor in quite that way before, so I felt pretty special. Anyway, Jack Rickard had sold me his net gain Warp 9 motor that was in the original Speedster, and had painted EVTV green. That's this motor here. And so I brought it back. It lasted about a month before I managed to kill that. And that was another video where I showed pulling apart the whole motor and pulling out the rotor and stuff to find out that the commutator bars had lifted, most likely due to an overheating incident. So anyway, so that one I had sent out and had it rebuilt, and just came back in December of 2012. So anyway, so this motor is back home again. So again, I originally purchased it back in 2010 with my first electric car build that was in actually that purple Daytona over there, and that was with my lead acid batteries and all that good stuff. Drove that around for winter and summer, and had a lot of fun with it, but decided I needed lithium, and so in July of 2012 I built the red car. Hopefully the wind noise won't be too obnoxious here. It is very windy today. So yeah, when Jack had this motor rebuilt out at Net Gain and Warfield Motors, he had him go ahead and replace the bearings with special ceramic bearings that are in here. So his intention was to test out the motor with those ceramic bearings and see, if it made a difference, if they were better with the heat, the thermal cycling that these poor little motors go through. So that is a difference with this particular motor. And another one is, as you can see on the input side, on the commutator side, so rather than having just the air holes like this, and of course this is the output, this is where there's a fan in here that blows air out and away from the motor, and so it's sucking air in on this side, on the commutator side, and so this band prevents particulates and salt and debris and crap from being sucked into the motor, but the downside of this is that then you actually have to pipe in air through this small hole and have enough volume that you're going to make up for the fact that it's blocked on all those other edges. So I'm going to have to either come up with a solution for this. I'd recently emailed someone about this whole topic and voiced how I didn't really like the idea of these bands, because if the system that feeds air to this motor gets, like the fan dies, or there's some problem, the filter gets clogged, that kind of thing, then all of a sudden your motor is going to be starved for air, and there's really no way of knowing that ahead of time, without constantly checking it, or having some kind of, extra wiring to check it or something, I don't know. So anyway, so my concern was that then the motor would end up getting damaged just from not having enough airflow, and it being artificially restricted by having all the hoses and the so forth on here. But I don't know, maybe I can come up with something clever. I've had a couple ideas bouncing around in my head about this since I got this new motor, this newly rebuilt motor, and so we'll give it a try. So anyway, that's going into the car, and so I'm going to have to pull out the all the adapter, transmission adapter plate and all that good stuff, and all this is going to come off and then gets put onto that motor there and then put into the car. So also, because this is a newly rebuilt motor and has new brushes, we got to do a burn-in for the brushes. So I'm going to be hooking this motor up to my battery pack and to the soliton, just like I did before, with the motor not connected to the drivetrain. So it's just free spinning out here on the floor, but connected with the cables. What that'll allow me to do is idle the soliton 1 for as many days as it takes, at a low amp draw, just enough to spin the motor, pick an RPM range that I want to have it at, and so forth. So this will actually serve another purpose. By draining the battery pack, which is now pretty much full, I'll be able to drain it down to empty and have the soliton automatically cut off the drain at a preset value, as I did in the previous experiment. So the idea here is that I'm actually using the soliton and spinning the motor, performing the function of seating those new brushes, also to deplete the battery pack down to empty, or what I'm considering empty, which is about 2.75 volts per cell, mostly automated via the soliton, and that's going to be kind of cool. We'll run that down, let the batteries come up a bit, run it down again, just idling the motor. And the purpose for that, of course, is that I need to re-bottom balance the entire battery pack, all 60 batteries, so that we can splice in this 60th battery. Sorry, there's 59 batteries in the pack currently. So the 60th battery, we can add it back in, and of course I will do a final battery bottom balance using the Power Lab 8, just to kind of get the rest of it off, so they're all exactly the same, at the same level according to the Power Lab. So basically the bulk discharge we're going to be doing through the motor, and then the final discharge for each cell hopefully won't take that long, just with the Power Lab to get them all on the same level. Once that's all done, we're going to need to recharge them, and that brings up another topic of the rebuilt or recently repaired Manzanita Micro PFC 40M. So this is my original charger. It's been back to Manzanita a couple times for repairs, but this latest one ended up not being too expensive. I think it ended up being about $150, give or take, and that includes the repairs, the parts, the labor, and the shipping back from Manzanita. So that really wasn't too bad. I was pretty happy with that whole setup, or that whole resolution to the problem. So instead of having to buy another $3,000 charger, $150 starts to not look so bad. Anyway, one of the things that I had done was, because I changed the plug to these larger Anderson 120 amp plugs, I sent them an adapter to get it back to the original plug that they use, so they could do testing and all that kind of stuff. Also, I figured it'd just be handy to have an adapter around, just in case I need to help someone out charging their car. If they've got the smaller Anderson, I think that's a 50 amp plug on their vehicle, they can use my charger with it. Or my other charger, which has these guys on there as well. So anyway, Manzanita once again made my charger happy, and I just want to let everyone know that it's all good. I have not had a chance to test it in the car. As you can see, it's still in the shipping crate that I had sent it back to Manzanita in, but yeah, it should be fine. They're pretty hardy little units, and as long as lightning, condensation, or other stuff doesn't blow them up, it's all good. So that was, in case no one's read the comments, the problem with this charger ended up being that, or at least our theory is, after I talked to Rich Rudman, is that it probably built up condensation inside the charger during one of our wonderful winter days, where it got just a little bit warmer, heated up inside the car, had some condensation, and then it refroze. So they had frost inside the charger. So then when it turned on, started charging, the frost caused a short and thus blew up the charger. So anyway, that's that's what it's looking like is going on. Again, projects for today, we're going to be pulling this motor apart, taking a look at the brushes, pulling all the other parts apart, just basically taking everything off the motor, transferring it to that motor, burning in that motor, seating the brushes on that motor rather, and draining my battery pack, and all kinds of fun stuff. So a lot going on. I will try to keep you updated as best I can, as long as the weather holds and stops pouring and being miserable and cold for May. Anyway, take care, and I'll catch up with you guys in a bit. Okay, so the first thing we're going to do is go ahead and remove the pressure plate, the clutch, the flywheel, the taper lock adapter, the transmission adapter plate, and the motor spacer ring. I've documented this extensively in a previous video, so I won't bore you to tears with that whole process. But I just wanted to show you that the way I do this is I've got a small piece of angle steel, just from a previous project, that I've wedged in. I'm not sure if the lighting is very good here, but there we go, that's a little better. So I've got it bolted to the adapter plate and just into one of the teeth on the flywheel. And so, since the starter isn't necessary anymore, some people actually remove the teeth from the flywheel, but I find it fairly useful to be able to do stuff like this, where you need to put a lot of torque on those on these bolts, but at the same time, not have the flywheel spinning out of control. So what I'm doing is the star pattern, just like I do when I'm putting it together. I'm just doing very small increments so that it doesn't bend the pressure plate as it's releasing the pressure on that clutch. So as we remove it, eventually that clutch is going to move, and it will be fine. So anyway, I'm going to go ahead and get this taken off of here, and we'll be right back. Alright, so with the pressure plate removed, we can now see the clutch. and I used the special clutch alignment tool to hold it in there so it wouldn't fall out while I was taking out the pressure plate. So now we can actually see, so the clutch looks to be in pretty good shape as far as I can tell. We kind of heard that rattle, and that seems to be coming from these little springs in here. But I mean, they look like they're intact. I don't see any damage to anything. So yeah, that's the clutch. So this is the Sachs, or Sachs actually, I think is how it's really pronounced, clutch, the disc, and this is the one that goes with the pressure plate. So I'll set that over here. Okay, so that reveals our handy dandy aluminum flywheel. And basically, we can see how it's all scored here from where we had that previous incident with the clutch. That was the spec Stage 3 Plus clutch that had broke a spring, and the spring kind of gouged out a chunk of my flywheel. But that was just on the inside here, not on the friction surface. Now the surface appears to have, let's just set my camera on the, let's back out of here a little bit. So the friction surface seems to have some crap on it. I'm guessing that's just clutch residue and stuff, but it doesn't appear to be damaged or worn. And you know, we may have had some clutch slippage, thus causing it to be kind of shiny and mirror-like. But the clutch does hold really well, and I haven't had any trouble as far as taking off and smelling burnt clutch or anything. So anyway, so the next step is I have to remove these bolts to get the flywheel off of here, and yeah, that's the next step. So I'll go ahead and get those loosened up. You can also see these are the Allen head bolts that are actually as part of the adapter plate, or sorry, as a part of the taper lock adapter. And so, and then in there you can actually see the end of the motor shaft. So basically you could take these out and then this whole unit would come out still attached to the flywheel, but there's really no point in doing that, or no advantage that I can see, other than maybe that this would hold. So maybe I'll loosen these. I think I might loosen these up a little bit while I've got it locked in place, and then that way they'll kind of be broken loose and will come out more easily when it's time to actually pull that apart. So anyway, I'm going to go ahead and take care of that, and I'll be right back. Okay, with all the bolts removed from the flywheel, I'm ready to take it apart, but I did want to make a comment. Notice how the spacing of these holes is kind of irregular around there. That's done on purpose because there's only one way that you can actually align this flywheel onto the crankshaft of the original engine to make it line up properly. All the bolts will only go in when it's in the perfect spot anyway, and I'm sure they did that for balancing and so forth. What I ended up doing this time, just to make my life a little easier next time I put this together, is I put a little mark with a Sharpie, just to kind of show where that lines up, and that'll kind of make it so I don't have to try every combination before I find the one that fits. So anyway, just a little time savings thing for when I put this all back together in a little bit. Anyway, I will go ahead and pry this off of there. It's fairly light, being aluminum, but it does have a steel starter ring around the thing, so it does make it a little heavier, and it's going to require two hands to pull it off, so I am going to go ahead and do that, and I'll be right back. Alrighty then, so with the flywheel removed, we can now see our taper lock coupler in all of its glory. And you can also see where the Allen head bolts, I removed them with this tiny little tool here. Again, I don't put a lot of torque on them because they're very small, and I don't want to break them or anything. So it's just a matter of loosening these up, and I already pre-loosened them a little bit, so they're super easy at this point. And yeah, so we're just going to go ahead and get that unhooked and pull that guy out of there. Now sometimes it's a little bit tricky because the metal kind of swells and so forth and is a little tight on there even with the bolts removed. So sometimes you got to work it a little bit, just kind of back and forth, get some leverage behind it, maybe a piece of wood or a long screwdriver, just to kind of give it that little extra push to work it out of there. But anyway, I'm going to go ahead and pull that out. Be right back. What is it they say about the best laid plans of mice and men? As you can see, I've had a little bit of difficulty getting the taper lock adapter to release from the motor shaft. So that basically, I think it's probably just due to the cold, the metal expanding, all that kind of good stuff. So even with all the bolts removed, it's still not coming out of there. So what I'm going to do is hook up, as you can see, my magic gear puller that I bought at the tractor supply store, and we're going to go ahead and use that to pop this sucker out of here. Now it's almost at the very farthest extent that this thing will go in. I don't know if you can see the we got about 1/4 of an inch that it can go in yet, but that should be enough to pop this taper lock adapter off, and should be good. So anyway, that gear puller I had purchased originally for this motor, which is what I used to take off the end caps for the rotor, and we may be doing that in a bit. So anyway, we'll go ahead and give this a try and see if this works. And with a rather sudden pop, it finally let go, and is now freely removable from the taper lock ring. So for anyone who hadn't seen a previous video, so this little cone-shaped ring goes on the motor, with the cone tapered out toward us, and then on the inside of this piece it's tapered so that it locks right onto that bad boy and actually causes it to compress. You can see it's got like a cut in it, and so it causes that cut to compress on the shaft and make a very, very tight fit. Now of course they have WD-40 all over everything at the moment, but and then there's a keyway in the shaft of the motor, which is going to be a pain in the butt to get out, but there's a keyway right there that slides into this keyway here and make sure that it doesn't spin at all. So the whole system actually works really well, and I've never had any slippage or incidents or anything. And that's the kit that came from Electro Automotive, and so it was about $800 for the kit, and that included the spacer ring, the adapter plate, and these two pieces, along with all the bolts and stuff necessary to put it together. I had to make the keyway myself, so I just took a piece of angle steel, or actually I think this might even be aluminum, and a little 6061 aluminum, and cut it to the right size, slid it in there, and put it all together. And it went together so easily, in fact, that when I first put it together in 2010, I didn't get any video of it or any pictures, because I was just like, well, I wonder how this works. Okay, this goes into here, and this goes into here. Oh, wait, it's done, and it's ready to go in my car. So, anyway, I had documented it in a later video of the whole setup, and yeah. So the only piece that's really custom to my car, to my Dodge drive engine and stuff, was actually the pattern on the flywheel, and the way that this little piece actually connects to the flywheel, just like the original crankshaft on the engine, as well as the adapter plate there that is the exact shape of my transmission. And so again, I had sent them just a tracing of what the bell housing of the transmission was, and a bunch of measurements as far as what the crankshaft piece looked like. on the front of the motor, and this is what I got, and it was all good. So anyway, I got that all taken apart now. Next step is to take off these 4 giant Allen head bolts, and we'll go ahead and get those popped out of there, and we'll be right back. Alright, so the motor is now free, back to its original status, more or less, where it doesn't have anything attached to the rotor. So the rotor is just spinning freely on its own now, and so now we can tell if there's any weird sounds, if they're coming from the motor itself, you know, whether it's a balancing issue in the rotor is my current theory. So anyway, we're going to give it a try just by hooking it up to our 12-volt battery, and here we go. Okay, so as you can tell, we're getting a lot of vibration, and the motor is just not happy. You saw how it did not spin very long at all after it came to a halt. That's definitely an indication that something is binding, and it's just not spinning freely. Of course, as I was filming, I noticed that I had forgotten to take off the RPM gauge ring there, so anyway, we'll go ahead and get that taken off, but it's definitely a problem inside the motor, and it's sounding more and more like a possibly like it threw some balancing putty, and like the actual rotor is wobbling. So that's going to chew up the bearings if the bearings aren't damaged already, and you know, is a problem. It's also not something that I'm going to be able to fix myself. I don't know of any place around here locally that fixes motor balancing issues. It'd be like a spin balance of the rotor, but honestly I don't know if there's any place in central New York, or you know, even up in Syracuse, would be able to do that. So that's why I bought the other motor from Jack, mainly just because I didn't know how much downtime I was going to have while I was getting the motor repaired, and I said, hey, might as well have one on hand because I have a habit of breaking them anyway. So, alright, so we're going to go ahead and pull the brushes at this point and take a look at those just to see how they're looking. I'm honestly betting the brushes are fine, but I guess we're going to find out if the rotor wobbling around there tore up the brushes, or if the brushes just kind of dealt. Well, I guess we'll see. Be right back. Alrighty then. So I've gone ahead and pulled out the brushes and taken a look at them, and they look pretty good to me. I'm no expert on the subject, but these are the brushes that actually came from this spot over here, and I'm trying to keep them in their original configuration here. But so yeah, they have an H2 on the one side, and on this side it's N for National, T300 610 50692, and as you can see, they've got a good radius on them, and they're worn smooth with some little striation marks, kind of like sanding marks on them. And I'm not sure how well the camera's making this out, but the patina on the commutator looks pretty decent to me. Again, you can see those same striations on them, but you know, it really, these don't look that worn to me. And so just as a comparison, we have a couple other ones here. So these are actually out of this spot here, are these two. And again, same kind of thing. Now there is a little bit of discoloration on the top edge there, but it's not really chewed off any more so than I would expect. It looks pretty decent. So anyway, so the brushes I think are in pretty good shape, but just with my unexpert eye. So the biggest problem is that as we turn the drive shaft, that it seems to be, it doesn't turn very easily, doesn't keep spinning after you remove power from it, and so forth. So, could be the bearings, could be, at this point I'm thinking the bearings are definitely kind of bound up there a little bit, but it's probably due to the balancing clay. There goes the wind again. I'll try it from this side. So the balancing clay on the rotor may have flown off due to an incident while the motor was spinning, hitting various potholes and stuff in the wintertime here. So that's currently the theory. Not a whole lot else I can do on the motor myself. We can probably go ahead and ship it back to Warfield and Netgain and have it rebuilt, but due to the just shipping hassles involved, I'm not sure if that's going to happen right away, and so that's why I bought the other motor, and we'll go from there. But for right now, I'm going to go ahead and slide these brushes back in place just to make sure they're all in the same spots they were before, and then figure out what the plan is with this motor. So in the meantime, we're going to go ahead and take a look at these other projects that I've got going on, and I'll be right back. Alrighty then, so I have the new motor hooked up to the car, to the soliton and everything, and the point here is to do the brush seating process. And what we're going to do here is reconfigure the soliton so that it'll continuously run the motor and limit the amount of RPMs as well as amps that it's sending to the motor during that process. So the idea is that we'll have a very fine control over how fast the motor is spinning while it's seating in those brushes. So anyway, I just wanted to show you how I had it kind of jerry-rigged up here. It's just sitting here on the pallet, and you can kind of see, I'm not sure if this camera will pick it up or not, but there is a nice shiny commutator in there. Everything's all nice and shiny on this motor. That won't last long in this weather, but yeah, so that's the motor. I'm going to try to give you a close-up of how this is set up. So we have the RPM gauge on there, which is essential for this particular test because the soliton will not idle the motor unless it has an RPM signal, because that's how it controls how fast the motor keeps spinning. Also, up here on the back, we see that I have my temperature gauge set up. So again, this is a little jobby out of a original Dodge Daytona temperature coolant sensor for the radiator. And so it's not super accurate, but it kind of gets the job done of giving a general idea of where the motor's at temperature-wise. But I wanted it hooked up for this test so that I could monitor all that kind of stuff on the laptop. So I'm going to go ahead and show you how the laptop configuration is set up, and I'll be right back. Okay, so now we're going to go over the software configuration that I use to set up the soliton so that it will idle the motor at an appropriate RPM and amp range to properly seat these brushes for as long as we can go. And also at the same time to prevent my pack from draining completely to zero during the process. So what we're going to do is use my Soliton EV display and data logger program, which is what you see here, which is available on my website, daytonaev.wordpress.com. It's a free program, something I wrote in Visual Basic, that anybody can use who has a Soliton and a Windows-based laptop or whatever. So I am working on an Android version of this same program, but the Android version is not finished yet, and therefore I'll be using the Windows one today. So the main reason why I'm using this program is because it shows the current motor voltage, motor amperage, RPM, and temperature based on how I've got it set up with pulling that data from the Soliton. Now the temperature is a little bit of a sliding scale. It's not entirely, perfectly accurate. I've got it calibrated based on this input 1 voltage that comes directly from the Soliton, and that's hooked up to that little temperature sensor that I showed you before, the coolant temp sensor from the original Daytona's radiator. So essentially what that does is as the temperature gets warmer, the input voltage goes up, and it's not really a linear process, but I have a linear mapping to it, at least in this program. So you calibrate it at a low value and a high value, and then the program kind of interpolates in between that to figure out what the temperature is. So again, it's not 100% perfect, but it gives you a general gist of the motor case temperature, because the sensor is physically sitting on the case, and so it's not the commutator temperature, which is really the more important one, but I don't have a very easy way of measuring that at this point. So anyway, that's what this little program is going to do for us. Just over here on the right hand side, these are the current settings that I have run my Soliton with, and nothing really too exciting. I've shown it before in previous videos, but it just kind of highlights what the settings are that I do as my daily driver. And so I've got the max pack amperage set to 750, and the motor voltage is at 170, which is the net gain spec. So I'm not going up to the 192 or whatever that Jack uses. I always keep it at 170 for better or worse. Max motor amperage, 750 as well. And the max motor power is 128 kilowatts. And so that's kind of calculated by the 170 times the 750, rounded-ish. So the slew rate is basically how quickly the controller goes from no current to full current, whatever your full current is set to for the motor. So in this case, 750 amps. So it takes 2,000 amps per second is like the rate at which it goes up, which means it basically gets there in a little under half a second. That seems to feel peppy enough to me without kind of jerking the clutch, so it feels like it's a good compromise for the weight of my vehicle and my lead-footed driving style and so forth. Anyway, so those are the settings that I had it configured at before, but what we're going to do is go into the Soliton website and configure specifically for this particular test, or the brush seeding process. So what we're doing is I've got the maximum motor speed set to 2,000 RPM, and the idle speed is set to 1,000 RPM. Idle motor current is set to 50 amps, and the others are the default, basically how it hunts for to hold that value. So for the batteries, I've got the max battery voltage at no current and at full current, both set to 162. Now the way I came up with 162 was I took my 59 cells in my pack and multiplied that by 2.75 and came out at 162.25 or something like that. So it's pretty close. And so the idea is it's going to drain the pack down until it hits that value, and at which point it's going to shut off the controller, or shut off the motor technically. The controller will still stay on, but So power will stop flowing to the motor, at which point the batteries are going to bounce back up, but the controller will have already terminated and it won't keep hunting back and forth. So this is kind of a bulk discharge. It's going to take those batteries down to 162 volts for the whole pack, at which point it's just going to shut off, and then the pack will bounce back up to wherever it's going to bounce up to, and then I will proceed to bottom balance it from that point, which is down to the 2.75 for the entire pack at rest. Whereas this is 162 at load, so it'll be 2.75 volts at load. Anyway, the load is the max battery current of 50 amps. That is the max it's going to pull, and the motor current, or voltage rather, we're left at 170. So I think that's fine. It's not going to be anywhere near that because it's so limited by the RPMs and by the current that the voltage is never going to be very high at all. So the max motor current is set to 50, and then the max motor power, I've got it at 10 kilowatts, which is the minimum that you can set it up in this configuration. I left the slew rate alone at 2000. So as far as the Soliton data logger program, I'm going to refresh the settings, and so that's going to just query what it's currently set to as opposed to what it was set to before. So that just shows us that same information that I just read out, but a little more clearly, easier to see on the screen. Okay, so what I'm going to do is actuate the throttle to bring the motor up to speed, because the way that the Soliton works as far as the idle is you've got to kind of ramp it up to at least the 1000 RPM that it's going to idle at, a little higher than that, and then it'll drop down and kind of hold that value, but it doesn't do it if you just turn it on. So like right now the Soliton is on and all these settings are in place, but it's not really doing anything. Alright, and so what we're going to go ahead and do is ramp it up, and here goes nothing. So I took it up to about 1500 and then let go of it, and as you can see, it's kind of hunting around. It's not exact, it's hitting 950, 960, kind of wandering in that general neck of the woods. But you can see that our motor voltage is only 6 volts. It's fluctuating between about 4 and 7, and the motor amperage is hovering right around 26 to 33, give or take, in order to maintain that. So it's not a lot of power going into the motor, and there we go. The pack voltage up here at the top, 196 volts is where we're starting out, which is basically fully charged, and we're going to let it run and just keep on chugging until we get down to the 162 cutoff, so which will happen entirely automatically without my involvement. I'll check on it from time to time just because I'm curious what it's doing, but in general it should be fine. So what I'm going to do is actually shut this all down, and then I'll start logging and start it all up again from scratch. So I burnt, it looks like 15 watt hours out of the battery pack, just during my little testing to make sure this worked before I started filming. But yeah, overall it seems to work, seems to do the job, and it's spinning that motor. But let's go ahead and take a look at the motor just while we're here. See, it's spinning happily away. RPM sensor doing its sensing, a little light flashing brilliantly. It's probably pretty dark, but you can see that very shiny commutator, which hopefully won't be quite as shiny by the time we're done with this whole process. And there's the temperature sensor. And so, yeah. So there we go. Chugging and whirring and sputtering. Alrighty then. So the motor has been running continuously now for almost 15 and a half hours. According to my Soliton EV display and data logger, we're at 195 volts, and we've expended 2,888 watt hours and 14.74 amp hours. Now, doing the quick math, that means that we've used almost 15 amp hours out of my 180 amp hour pack. So this is going to run for a really long time. So the motor is pulling about 5 or looks like between 4 and 6 volts, and the amperage is fluctuating between about 33, that's a 26 there, on up to 41. So the motor RPM is still hovering in that looks like 940 to 980 range, something like that. And the motor temp is 71 degrees. Again, that's kind of a rough estimate. You see that the Soliton has heated up to 98 degrees. So we're now up to body temperature almost. And it's not enough for the little fans on the Soliton to kick on. There is no airflow across the Soliton other than just ambient temperature in the garage here. But it's not overly hot in here anyway. I'm guessing it's probably 60s outside today. But anyway, so this is still chugging along, and looks like it's going to chug along for many more days. And that's good. That's actually what we're looking for. We want this motor to get these brushes nicely seated, and before we put any serious current through them. I'm not sure if the camera is making this out, but in the bottom right hand corner it popped up that it's detected my Daytona EV wireless network. That is how the laptop is connected to the car, is just with the wireless router that's in here. Anyway, so that's pretty much it for right now. We're going to let it just keep on chugging, draining my batteries ever so slowly, and at the same time, seating those brushes. So anyway, here's what the motor is looking like and sounding like right now. 15 and a half hours into the brush seating process. Just figured I would document this at this point. I know it's kind of loud and obnoxious, but here you go. So it's hard to tell with my camera and such, but the sound definitely seems to be a bit better than it was when it first turned on. A little more smooth and not quite as obnoxious. But anyway, that's it for today. I'm going to let this chug and whir and sputter for the next several days anyway, and I'll give you guys all an update as soon as there's some kind of interesting things to report. Take care and have a wonderful day.